Okay, this is just a short video reviewing graphing transformations of sine and cosine. Graphing transformations can be a bit challenging at first, so it does take practice. We'll just do one example in this video. So actually we're going to try graphing a transformation of cosine. Before we do that together, let's just briefly review what we do know about possible transformations. So I've went ahead and set up just a very general cosine curve. You can see I've picked on cosine here, but anything we're about to say is true if it were sine as well. So there are really four possible transformations we're looking at. First, we could have a change in the amplitude, and that's this coefficient out front of the trig function. And amplitude is really a measure of the vertical distance covered by the graph. So if the amplitude changes, the graph would be either stretched or compressed in the vertical direction. Interestingly, if the value of a is greater than 1, that's what will cause a stretch. And if the value of a is less than 1, that's what would cause a compression. You'll notice I'm using absolute value bars because amplitude is like a distance, so we wouldn't want a negative distance. But if a were negative, it would mean you'd have that vertical stretch or compression if the value was other than 1, and it could possibly have a reflection. Again, that would be if a is negative. This b value here really controls the period of the graph, which is related to how long one full cycle takes in the horizontal direction. We have to be careful though that the period is not b itself. The period, I'll just jot this over on the side here, of the graph is actually going to be 2 pi divided by that b value. So we have to be a little careful with that. But the period, similar to the amplitude, controls stretch or compression in the horizontal direction. And if the b value is less than 1, that would cause a stretch. And if the b value is greater than 1, that would cause a compression. Notice that's opposite of what happened with the vertical stretching. So I like to think about it as if I'm driving slower, it will take me longer to get there. That's what's happening with the stretch. And then if I'm driving faster, it will take me less time to get there. So that's the compression. So vertical stretching, compressing, and horizontal stretching and compressing are maybe kind of new compared to algebra in some ways. So these last two transformations will be a bit more familiar. We're looking at this value of c here added to the argument within the parentheses. That value causes a horizontal shift. So if c is positive, the shift is actually in the left direction. And I'm going to be good and use words just like I've asked you all to do. So if it's a positive c, it shifts left. If it's a negative c value, it will shift in the right direction. And then our d value, kind of all on its own outside of the argument of the trig function, that causes a vertical shift. If d is positive, the graph will shift up d units. And if d is negative, the graph will shift down d units. So those are kind of the different things we're considering. Just as a reminder of what could happen. So let's try applying these ideas in the context of an example. We'll run through one possible strategy of many for graphing these transformations. So again, I'm going to suggest a possible way to create this graph, but I highly encourage you to practice on your own and see what makes sense to you. There are many different ways you could go about this. So with our previous conversation in mind, we are now being asked to graph y equals 3 cosine of the quantity x minus pi over 2. And I'm going to go ahead and start color coding these pieces. So this 3 out front, we just talked about that coefficient out front being the amplitude. So the amplitude of this graph is simply 3, since the absolute value of 3 is 3. Now, you might be inclined to say the period is nothing or something like that because there's not an obvious b value. But let's go ahead and get something in there to make that b value feel a bit more existent. If I had just 1x, right, that's the same as 1x. So that means our b value is 1. It's very common for people then to say that the period is 1, so be a little careful here. The period is always, for sine and cosine, 2 pi divided by the b value. So in this case, the period is just 2 pi. That basically means there's no horizontal stretch or compression compared to the base cosine curve. Let's see, this next value, this minus pi over 2, I'll go ahead and highlight that in green. That's inside the parentheses, so that is going to be a horizontal shift. And in this particular example, you'll notice that since the b value is 1, factoring out the b value doesn't change the c value. But if the b value is other than 1, just be really careful to make sure you've identified the proper horizontal shift. In this case, everything I just wrote wasn't needed because factoring 1 out didn't change anything. So the horizontal shift is, let's see which direction. It's going to be right by pi over 2. So since it's a minus pi over 2, that tells us to shift it right. And I would encourage you to use the words right and left, just so it's very clear. In terms of a vertical shift, I don't see a d value like we had talked about. The d value would mean I'm adding or subtracting a value outside of the argument. But in this case, you can see there's nothing out there. So there's actually no vertical shift. Perfect. So notice that we took a few minutes discussing those characteristics. I think that discussion will make the actual graphing process a little smoother. So definitely talk about those 4 things before you dive into the graph. But now I'll just go ahead and start getting some space ready to graph on. And let's see, we're about to graph a cosine curve. So the strategy that I shared in class, which again you can take it or leave it, but if you're trying to find a method for graphing, I always like to start by graphing my base function. And in this case, that means to me, let me just get a cosine curve on the graph and I'll adjust it as needed to meet the 4 conditions here. So when I think about cosine, cosine starts at the high point of 1, and then I'm going to just kind of space out our special values here. So then cosine would fall to the midline. Halfway through it would be down to its lowest point. Then it'd be back up to the midline, and then it would reach its highest point again. So I'm going to simply connect those 5 points I put down. Notice I haven't labeled yet horizontally or vertically, but I think you all would agree that this is the base shape of a cosine curve. So we want to be really familiar with the base graphs of both sine and cosine. How would it be different if it were a sine curve? Well, a sine curve would actually have started at 0, 0, right? So the base sine curve would have been in a slightly different location. So if you agree that that's the base cosine curve, now what I'd like to do is just walk through the 4 characteristics on the side and see how I need to update my labeling and possibly see if I actually need to move the graph. I'm just going to go in order. So let's start with amplitude. I need the amplitude of this graph to be 3. Well, without doing any moving of the graph, I can simply call my highest value 3, my lowest value -3, and I should be good to go. So caring for the change in amplitude, the stretching out of this graph was actually pretty easy because I just made my vertical labels match that accordingly. So that's good to go. I also need this graph to reflect a period of 2 pi. So since I'm starting this graph at 0, that means the ending point for the full cycle we're showing needs to be 2 pi. So I kind of like to get my first and my last tick marks up there. And the way I go about getting the labels in between, I just like to say, all right, if this end label here is 2 pi, then halfway in between would be half of 2 pi, which is pi. And then halfway between 0 and pi sounds like pi over 2. feel free to use your unit circle. So then halfway between pi and 2 pi, that sounds like 3 pi over 2. Your unit circle can really help you get those values, but really they're just the quadrantal angles. So we're just walking around our axes. So take some time and make sure that makes sense to you. Or please ask, because I could show at least 2 or 3 other ways for coming up with those labels. So I feel pretty good that our graph reflects the amplitude of 3 and the period of 2 pi now. So we're getting pretty close. The next thing we need to make sure is that our graph has a horizontal shift from the base graph that's right by pi over 2. So horizontal and vertical shifts actually mean you're picking up the graph and moving it. So in this case, it's a horizontal shift. Every single one of my 5 points that I've labeled on the graph need to pick up and move right by pi over 2. Conveniently, in this case, my tick marks already measure pi over 2 units. So this first point, which was at 0, 3, needs to move by pi over 2 to the right, and it will now be sitting at pi over 2, 3. This point at pi over 2 moves to the right, and it now sits down at pi. This point at pi, when it bumps to the right, sits down at 3 pi over 2. The point at 3 pi over 2 bumps to the right, sits at 2 pi. And this last point needs to bump as well, and we need to discuss what that new horizontal label will be. So let's see if we can come up with a good description of this point. Basically, my labels so far sound like 0 pi over 2, 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, so this one must be 5 pi over 2, because my tick marks were just measured by 1/2. So again, we really had 0 pi over 2, 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, so then hopefully that makes sense that the next label would just have been 5 pi over 2. Notice that 2 pi over 2 reduced just to pi, right? So we reduced that one. Similarly, 4 pi over 2 reduced to 2 pi. So a little bit of fraction work there. So what I need to do now is connect the green points, and that will then, I believe, be our final result for this curve. So we'll connect those green points, and let's make sure we agree that's our final result. We took care of that horizontal shift. The last thing is this vertical shift says do nothing, so that's pretty nice. That means to me that the green curve we've shown is the end result, what we really care about. And that green curve is the final graph for y equals 3 cosine of the quantity x minus pi over 2. So my graph looks pretty messy by the end, but what I would be looking at in reviewing your work is the final solid graph, right? So my attention is really on the green graph that I've showed here on the screen. The black dotted line was used to help me get a feel for the base cosine curve. We updated our labeling accordingly, and then we actually had to bump all our points over. So this is one way you can graph transformations of sine and cosine. You can plot the base curve and then make adjustments. But if you're interested in another way, just ask and we can surely talk about some options. I hope this helps.